So my advice, which carries over from last time, is don't overcomplicate the problem. If you got a mosquito on your arm, you're not going to pour acid all over yourself. You're just going to swat the mosquito, right? So, do we need the quotient rule on this problem? No. Do we need the quotient rule on this problem? It is a function divided by a function, so we'll see. Do we need the quotient rule on this problem? No. Okay. So just make sure that you take a look before you leap off the cliff, okay? If I rewrite this as y equals 5/8 times x to the fourth, then clearly I don't need the quotient rule there, okay? I can take the derivative and I get y prime equals 20/8, which is 10/4, which is 5/2. 5/2 x to the, right. Okay, for the second one, we do have a function divided by a function, but let's distribute that 3 in, and we get y equals negative out front 9x minus 6x squared over 7x. Yeah, I could use the product rule.
Yeah, shouldn't it be plus 6x squared if you're distributing the negative in?
I actually didn't distribute the negative in. I just screwed up the way that I wrote that. So let's make that, okay, now it's distributed in. Thanks. But I could rewrite this again as y equals negative 9x over 7x plus 6x squared over 7x. Why would we do that? Because now when I simplify this, I have y equals negative 9/7 plus 6/7 x. And now I can take the derivative, which is y equals, the constant just goes away, and the 6/7 x turns into just 6/7. There's your answer. So, again, watch out. There's going to be a clue if you just have one term in the denominator. You can separate that out into separate fractions. For the last one, I also want to rewrite this as what? Times x to the negative second power, that's right. So now we can take the derivative, y prime equals negative 18/5 x to the negative third, which becomes y prime equals 5x to the third. Good. So in all three of these cases, we rewrote in order to make the problem appear simpler to us so that we could use not the product rule. Or the quotient rule. Yeah, that's what I meant. Thanks. So find the derivative. Technically, we don't know what the derivative of this is yet because we've never worked with it. But we can find it. That's exactly what we have to do. So tangent x is sine x over cosine x. Right? Or is it cosine x over sine x? Okay. All right. So that's good. At least we know that. So we have sine x divided by cosine x, and I want to take the derivative of it. So what do? Quotient rule. Y prime equals? F prime g minus g prime f, right? Over g squared. Okay, so f is the numerator, g is the denominator. So f prime will be what? Cosine x times cosine x, okay, minus, this is f prime, this is g, minus g prime, which is negative sign, so I'm just going to include parentheses, times the original f, which is sine x, all over at that beautiful straight line. G squared. So cosine x squared. I'm writing it like that for a reason.
It's not cosine.
Yeah, cosine x squared is the same as cosine squared x. We know that. But I'm writing it like this for a reason. It's kind of like not foiling the denominator. Okay. All right, so now we're going to simplify this. Y prime equals cosine x squared minus plus sine x squared all over cosine x squared. Split them up. What do you mean?
Like fraction.
Oh, so you want to make cosine x squared over cosine x squared, which would reduce down to 1. And then you'd have sine x squared over cosine x squared, which would reduce down to tangent squared.
1 plus tangent x what?
Something's fishy here. Actually, there is an identity going on, but not that one. You can use that one, but this one is the better one to see right away. If I rewrite this as sine squared x plus cosine squared x, which is what that is, over cosine squared x, the numerator becomes what? 1. So now we have 1 over cosine squared x. What is 1 over cosine? Is it? Secant. So this is y prime equals secant squared. Hopefully that's right. Take a look on the inside cover of your book. Look for tangent. The derivative of tangent is what? What? Yeah. So what you are seeing is something that we're going to learn pretty soon called the chain rule there. They're going to express everything on the inside cover of your book in terms of the chain rule. U is whatever this function is sitting right here, in this case x. So it'll be secant squared u, which is x, times the derivative of u, the derivative of x is 1. You'll learn the chain rule here pretty soon. So when you look on the inside cover of your book, you'll see just u's. But all that means is this in this case. The derivative of tangent is secant squared. Okay. All right. So again, now that we know the derivative of tangent, we can use it. The derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of tangent is secant squared. Moving on, higher order derivatives. As long as there's an equation that you're looking at, you can take the derivative of it. Doesn't matter if it's something you've already taken the derivative of. You can take the derivative of the derivative. And then if you still have a function, you can take the derivative of that. And you can just keep going until you either have no function anymore, meaning everything has turned to 0, or you get bored, or you die. Repeatedly taking the derivative after derivative is what's meant by finding higher order derivatives. So it's not just a first derivative anymore. We actually never have called it the first derivative, but when you take the derivative of a function, that is the first derivative. Take the second derivative of a function, and that is taking the derivative of the derivative. Finding the third derivative, which is what this example is trying to get you to do, means you need to take the first derivative, and then you need to find the second derivative, and then you're going to find the third derivative. Okay? The notation for that is just additional primes. So if I have y is my first function, then my second function will be y prime, my first derivative. My second derivative will be y double prime. And my third derivative will be y triple prime. From there, I've seen books that go into Roman numeral notation, so they treat the primes as actually i's, the capital I's in Roman numerals. And we'd have to the IV, that would be Roman numeral 4, and that represents the fourth derivative. I've also seen books that just go with a number 4 in parentheses. And I believe that's what our book does. Okay? What that means is the fourth derivative. So, we have find the third derivative of y equals that polynomial. The first derivative is found easily enough. Y prime equals what? 6x². All right, so that is the first derivative. It tells me what? The slope of the function at any given point. I use slope in quotation marks there. What it really means is the slope of the tangent line at any x value along the function, right? Always keep that in mind. So now I can find the second derivative, y double prime equals and what does that tell me? No. It does tell me the slope of the tangent line of... Nope. What did this one tell me? The slope of the tangent line anywhere along the graph of this. So then this tells me the slope of the tangent line anywhere along the graph of this. It actually tells us more than that. No, it's not the slope of the slope. The slope of the slope is just the slope. That's not what it does, okay? You will find out very soon that there is more going on in the second derivative than just that. There's more going on in the first derivative than just what we just said, okay? That comes along in the next chapter. We need the third derivative, though, so I need y triple prime equals what? 12. And that would be the slope of what?
No, slope of the tangent line anywhere on the graph of y double prime.
Right. Now look at this. What kind of graph is this? It's a line with a slope of 12. So doesn't it make sense that if you took the derivative of that equation, you'd wind up with 12 as your answer only, unchanging, okay? Incidentally, what would the fourth derivative of this be? 0. Why would it be 0? Because y equals 12 is a horizontal line. It has a slope of 0, okay? So if you take the derivative, you wind up with 0 because it tells you the slope of the previous equation, okay? If the position function is s of t, we talked about position and velocity. And the derivative s prime of t is equal to the velocity. Then what is s double prime of t going to be equal to? V prime. That's right. So s double prime of t equals v prime of t, which is what? Think back to physics. You have position, you have velocity. Yeah? Without numbers, you don't need numbers. What is gravity? No. What is it? It's acceleration. A of t. An acceleration function. If you take the derivative of position, you get velocity. If you take the derivative of velocity, you get acceleration. Okay? All right, so we have the velocity of an object in meters per second is v of t equals 36 minus t squared. Find the velocity and acceleration of the object when t equals 3. So I'm giving you the velocity equation. Okay, we could do that right now. V of 3 equals 36 minus 3 squared. So that's 36 minus 9, which is 27. What? Thank you. Meters per second. Yes, it does tell us it's meters per second. All right, so the velocity at 3 seconds is 27 meters per second. What is the acceleration? How do I find that? Right. V prime of t, which is the acceleration, A of t, is going to be what? Negative 2t. So now I want what? Plug in 3. V prime of 3 equals negative 2 times 3, which is negative 6 what? Meters per second?
Where did you get negative 2t?
We took the derivative of the velocity function here. V prime of t equals, the 36 disappears, we have negative 2t squared. The 2 comes down, negative 2t to the first is negative 2t. It is meters per second squared. Meters per second per second. What can be said about the speed of an object when the velocity and acceleration have opposite signs? It will slow down. Not eventually. It is slowing down now. So the velocity of this thing is 27 meters per second. The acceleration of this thing is negative 6 meters per second. I don't care what direction this thing is going, up, down, left, or right. The acceleration is going the other way, which means the object is decelerating. Okay? So what can be said? The object is decelerating. E-L. Decel. Excel. Decelerating. What I want you guys to do is take a look at this graph that I've given you. And I want you to figure out which function is f. Which one is f prime and which one is f double prime. And you need to tell me that not assuming anything about this graph at all. Which one is which? Half an hour, you could probably come up with it.
Do they give you half classes?
Yes. You cannot assume ever anything about any graph that you're given. Never. Doesn't matter if it looks like a cubic and a quadratic and a linear function. You can't assume. Because this quote-unquote line right here could, off the window that I have given you, do this. Suddenly it's not a first-degree polynomial anymore. It's something totally bizarre. Okay? That would change everything, right? So you can never assume anything. The correct order here is, this is the original function, the green one is the first derivative, and the blue one is the second derivative, as you probably guessed, because you were looking at the degrees of the polynomial and you know what those graphs look like. But you have to figure out what the graph is telling you, not what you are assuming from the graph. The graph of the red line, or the red curve, is a positive slope here up until this location here, at which time the slope is definitely 0. I don't know if it's exactly at the y-axis, but I know that right in here the slope is 0, okay? Which other graph shows me that I have a slope of 0 in the original function if I'm looking at the graph of the derivative function? Assume that it's the blue one. This tells me that when my original function is around 0, I have a slope of -4. Is that the case if the red one is my original function? No. I have a slope of approximately 0. So if I have a slope of approximately 0 and this is my original function, does that give me a slope of approximately 0 in my derivative function when I graph it? Yes. Okay. So if this is the original and this is the derivative, then this sort of matches up. I have a positive slope here. My points that I would be plotting are all positive values for each of those sequential x values until I get to here when that slope turns around and starts going negative again. Now I will go back to my green function. Now I'm plotting negative values on my derivative function, which is telling me that I have a negative slope on the original function until I get to here. Then I have sort of getting smaller and smaller negative numbers until I get back to 0, just like my slope would be getting less and less until I get back to 0 here. And then it takes off positive again. So then we're back on the positive side, plotting positive y values again, okay? Remember that the slope of the derivative tells me the slope of the original at any point, okay? If I graph all of those slopes, I get that function, some sort of quadratic polynomial, okay? Now take a look at the green function. I have a negative slope all the way through until I get to here. The derivative of the green function would be the blue function. I'm plotting negative y values all the way until I get to here, and look at that. They line up, okay? I have a slope of 0 here. I have a value of 0 here. And then the slope turns around and becomes positive. I have positive values here. If you try to do that analysis for any of the other combinations of functions that we have here, they won't work. This one must be the original, this one must be the first derivative, and this one must be the second derivative from that analysis, and only that analysis. Nothing else will be true.